Welcome, Sudhir sir. Hello. Welcome, Sudhir garu.
Yeah. Hello, madam.
Yeah, we'll start at exactly 2:15, sir.
Sorry, ma'am.
We'll start at 2:15 exactly.
Okay, ma'am. That will work. Ma'am, can you see my screen?
Yes, yes, Sudhir. Yeah.
Okay, ma'am. Thanks.
A very good afternoon to everyone present here. Today, we now introduce our next speaker, Mr. Sudhir, graduated in BTech EC, worked for about 10 years in IT industry in EMRI, AGS and Next, have been granted a patent in locomotives in year 2012, awarded TIP Fund by DST GOI. Co-founded iMake, a young growth company primarily into engineering services with focused product development with in-house design team, rapid prototyping, injection modeling, and CNC. iMake primarily has clients from electronic industries, defense, and film industry. During the COVID lockdown, iMake has been given opportunity by DRDO for developing medical PPE, ventilator accessories, and sterilization unit. A warm welcome to Mr. Sudhir. Thank you.
Hi. Thank you. Thank you very much. So, yeah. Right. All right. Let's. May I know what's the kind of audience? Primarily, most of the people are faculty. You're comfortable with English, or everybody's comfortable with English? I believe. Is that right?
Yes, sir.
Yes.
Yeah, that's all. They need English only.
Yeah, and most of the people are faculty, or there are other students as well. Most of the people are faculty, is it?
Yes, yes. Most of them are faculty only.
Right, great. So I'll quickly. Yesterday I had a discussion with the Mali madam. So I asked. I took some advice from her, and what I believe is better is I will run through quickly through these slides with general information which we think is relevant in the current day. Many of which you might be knowing it or covered by other speakers. So and then I would want to run you through. Let us have allocate more time towards a discussion at the end. So wherein we can discuss the recent products that we made in the last 1.5 years. So I will run through the entire cycle, as in from the concept stage to the design stage, and then to how we 3D printed that, what changes we made, and then we went to the injection molding stage. So you'll get a full picture of that. Is that fair enough?
Yes, Sudhir.
Yeah. All right. Okay. So, all right. Okay. So, as we all know, there are many manufacturing methods, obviously. So, one of them very frequently that we use is sheet metal. And sheet metal has been there for quite some time that we've been using. So sheet metal has some advantages and some disadvantages. So these are the advantages and disadvantages which many of the faculty must be knowing for sure. So I will go through these things. I mean, just to give you a very brief thing, to make a sheet metal part in very detail, you would need a punch and die, and that would typically have a pretty long lead time to get it done. So to get this done, unless you really have a large scale volume, it doesn't make sense to go for a sheet metal die punch, getting it done. Sheet metal, or even forming for that matter, or even deep draws of many of you must have used metal bottles these days. They are deep drawn. They are also made using sheet metal primarily. Okay. And then you have CNC. It has very high accuracy. Like, I mean, if you talking of all of your watch components, they're mostly machined or they are done using CNCs. And metals, woods, and plastics can be done. And the repeatability is pretty high, as in the first part and maybe the 10,000th part also will have the same kind of an accuracy. Your MacBooks are machined, your Apple iPhones, the outside rim is machined, or majority of your internal components in your watches or the engine heads in your vehicles are also machined. Okay, and it is expensive for even for mass production unless you have very high volumes. It doesn't make sense to get it done through CNC machining, and the lead time is pretty high. As in, to get a medium complexity unit also, the normal market time at the moment is about anywhere between 6 to 12 weeks of time. And the current fast-paced environment, people don't have that kind of time. Reason being, the product lives itself have shrunk. I don't know. I mean, most people these days don't use the same phone that they use for more than 2 years. They don't use the same laptop for more than 4 or 5 years. The car is changing like 4 or 5 years. Now, if you add a 6 months or a 1 year of product development in the life cycle of the product, then the companies would lose a lot of time. Okay, so they will have to do things parallelly or invent new ways of doing to deliver and reach the market faster than normal. And then you have sand casting, which is also a very old method. Many of your large metal statues, or even your some part of your large jewelry, or even some components in automotive are normally sand casted. Like your base, the chassis is sometimes sand casted, not exactly sand casted, but sand casted mostly. Sometimes they're investment casted, sometimes they're laser cut, but there will always be a combination. So the advantage is you can do it in much smaller batches. And yeah, by the way, railway components largely are sand casted. Many railway components are done in Hyderabad as well. If you go to Medak area, there's a huge number of companies which do sand casting. Okay, the surface finish and the porosity is often a problem, and the initial pattern is still required, but then the lead time is relatively faster because you're making it like a copy. So you have an original part, you do it in wood or you do it 3D printing, and then you make a copy of that. So that's the most the quicker way to do in metal is sand casting. Like you have lead times, you can shrink it down to 1 week kind of a lead time. Yeah, and by the way, please don't hesitate to stop me at any point of time. And also, so I'm not from the teaching background, so I would not be a good teacher. So please stop me if I'm going fast or going too slow. And investment casting these days, okay, just to make it fun, I mean, how many women are there in the audience? Just to make it interactive, because I don't see people reacting anything. So how many women are there in the group? Approximately half of them. Hello.
Yeah, we raised the hand.
We are raising the hand, sir.
Oh, you raise the hand? Oh, okay.
Yeah.
Oh, yeah. Where do I see that? I'm new to this. Oh yeah. Now I can see. Okay. All right. So good number. Okay, good. And all right. So a tip for you: next time, whenever you go to buy jewelry, if the jeweler says that it is handmade, he's talking nonsense. Okay, he's just trying to trick you. 90% or 95% of the jewelry made currently is entirely using investment casting, and the primary part is made using 3D printing. I've seen a couple of jewelry manufacturers in Mumbai and in Ahmedabad. They literally make thousands and thousands of models every single day. I'm talking of thousands in a single day. Okay, and the production cost in jewelry has actually come down after using 3D printing. If there are two areas where 3D printing has made a big impact, one is jewelry, the other one is medical implants. Okay, and your handwork, your antiques, all of them are at all times now are made. The artisans have almost died now, so you don't have anybody doing by hand. All of them, you take Malabar, you take GRT, they have their own setups. Everyone, every unit has their own jewelry setup. Okay, and then coming back to investment casting. So investment casting, it has a very high accuracy and a good surface finish. That's the reason you do it for jewelry. And also, just to give you a reference, we do a lot of work for this Telugu film industry and a little bit for Tamil and Hindi film industry as well. Many of this custom jewelry that they wear or these things, they are also done using investment casting. And before investment casting, like for example, if you're seeing this part, the blue part that you're seeing where I'm pointing, this part is 3D printed again. Okay. And it's very economical and very fast method to make the part that you design, you 3D print, and then you make using investment casting. In this case, I've been doing this only single part because it was the first part. But typically in a single tree, you can make about 60, 70 such pendants in one single go. Pendants or your ring. So this is again used in different places. Okay, these are called motifs. So yeah, all right. And then you also have injection molding, which I'm sure most of the people must have seen it. I'm assuming. And then you have additive manufacturing. It is obviously you can do a single unit. Okay, like for example, if you have 50 different designs to be made in a single go in a single 3D printer, you can do all 50 at a time. And that is how the 3D printing has been helpful for medical and jewelry, because it is many times customized and the orders are not bulk. Okay, and one more business aspect, business advantage that 3D printing has given to jewelry industry or medical industry is they don't have to maintain huge stocks. Because of the short turnaround times, the parts are made on order, and within a week you will get your part. I mean, many of you must have used, must have heard of these dental implants or your knee implants. Knee implants are nowadays being mass manufactured, but dental implants largely, if there is a crown or if there is a custom thing, they are being 3D printed using various metals. So that's one. These are the two industries which made maximum utilization of 3D printing. Okay, and yeah. Oh, these are the various 3D printing methods that you have. I'm sure you guys must have seen this a lot of times, but let me quickly go through the larger sections. You have something called as a VAT polymerization. VAT polymerization, wherein you, just to put it in layman's term, you pour a liquid and the liquid is cured by a specific frequency of light. When this specific frequency of light hits it, like for example, the machines that I have is 456 nm. So the moment light of that frequency hits it, it becomes solid. So the light travels in the path of the object, and then slowly layer by layer, this gets cured. And you have DLP. In DLP, you have again various types, wherein there's a screen, you reflect an image. You project an image onto the VAT, and that VAT layer, wherein there's a liquid, that becomes solidified. So again, there is this CDLP, which is a relatively new technology, but it is giving much faster results than the other two. And your entire jewelry or your hearing aids, there are some customized hearing aids that are made. Even those things are all made using VAT polymerization only. There is no other technology that these guys use. They always use VAT polymerization. And then you have material extrusion, wherein it's called FDM, which you guys must have seen a lot of time. I believe there is a 3D printer in OU. I mean, there are a lot of 3D printers rather. Am I correct?
Yes, sir. Yes, sir.
Yeah. Okay. All right. Yeah. So, and then you have metal jetting, which is largely these days led by a company called HP. MGF and MJ, both of them are largely led by them. And this is again a slightly different technology. It is initially done by a company called Objet, an Israeli-based company. The challenge with this one is this technology didn't take off as well as it should. The maintenance of these machines is pretty high. I know at least 2 machines which got spoiled, and each machine is about a 1.5 crore kind of a cost. And you get great quality. The beauty in metal jetting is, unlike any other manufacturing method, here you can make a digital material, as in you will have a single piece which is harder on one side and softer on the other side. You can tune the machine to that level. So these are possible in machines like Objet, wherein they do a metal jetting, as in like inkjet printer. They throw various kinds of various types of materials, and then that gets cured. So very unique technology, but and very specific applications that it has, and but it didn't make that much into the mainstream industry, or it's not being used as much. Binder jet again is a different this technology. This and powder bed fusion are very widely being used, as in basically these are used. The material is joined using a liquid, and a combination of these two technologies is also being used recently to make ceramic components. Normally, ceramics are said to be a very, very difficult to manufacture. So there are a couple of companies which have cracked on. They made powders which are ceramic infused, and there is a binder jet, and then it is cured. So that is with a combination of, it's between binder jetting and powder bed fusion. And powder bed fusion, even OU Lab has this. I think they have OU Lab has this EOS machine. So this is one of the most reliable and time-tested method to get very high quality parts and at a reasonable price, and very good repeatability is available in this. And then you're talking of, let us say, metal sintering. There is only, I believe, a handful of machines, installation base in India, which is this SLM. So these machines are, mostly by German make. There's a company called SLM. They lead the market, and then there's a Rainshaw, but mostly SLM leads the maximum market. So this is also a very these components are being used largely in satellite components or aviation components, where it is very complex to make in traditional methods. So there it is being used. And then you have the EBAM technology. The EBAM technology, or lens is also a very fused with laser, largely common with this. This is still not into very much mainstream. If you go to EBAM, the advantage of EBAM is the powder is melted using laser, and it is melted very near to its actual melting point. And because of that, the properties that you get out of this 3D printed component is the closest to its casted or its virgin material properties, because of which these components are being they're being widely used in aviation or even aerospace, the space applications, and even also in implants also, because the properties, whenever you use, like for example, in any of these components that you're looking at, like if people are calling it as an ABS material using FDM, or people are calling it as PLA material, or whatever material they're calling, the same ABS material, if you actually make using injection mold, the quality is much better when you compare that with a regular FDM method or a 3D printed method. But EBAM has a method wherein which they were able to crack it such that the material properties are very near to the real ones. And then you have LOM. This is also a very rarely used technology, wherein there is a paper-based technology wherein with papers the components are made using layer by layer. Paper is cut and glued, and then similarly you do composites, which is carbon fiber and stuff like that. So these are the LOM is also not into mainstream. Actually, this company Emcor is it's on the verge of. This company has gone bankrupt because they don't have any much takers in the market. Okay? So these are just a brief about all the technologies that are available within 3D printing, and this is not a comprehensive slide. You can find all these details in much more detail in 3D Hub's website. So that's where we have taken the data from. Okay. So yeah, and then general things that you should probably know is, again, when you're designing, especially because you're from biomedical engineering or you do a lot of electronic stuff, is you should understand what is an ingress protection, which I'm sure must be part of your syllabus or you must have already been knowing, but I'll just go through it again in a minute. Ingress protection is the protection that, your phones these days or your laptops these days are being claimed to be an IP67 or an IP56 thing, wherein which determines the ingress level. Ingress as in what can penetrate into the device. Okay. Now, if you're talking of IP68, the first letter denotes the protection against the dust. The second letter in this denotes the protection against water. That means if you're talking of IP50, it means it is dust protected, full contact protection against dust deposits inside, but it has no protection against water. If you're talking of IP08, then there is no protection for dust, but there is a protection against water, which is a rare case, because if you protect against water, you'll by default get some dust protection as well. So that's the reason most cases you will see numbers from IP54 to IP68 is what is the combination that you will see, because when you are protecting all sides of your equipment, whether it is a biomedical equipment, whether it is an electronics equipment, whether it's a phone or any other even toy, whatever you're making, whatever you intend to make, it is supposed to be with this. And the reason why I'm sharing with you this is that if we are not aware of this thing, I know many products which are who came to us for product development, and their specific industries needed this IP protection, which they realize at the fag end of their product development, and they will have to redo a whole lot of stuff. As in, like for example, I'll give you an example. Like for example, there is an electronics industry who are primarily installing for the street light monitoring system. Okay, now what they have done is they didn't even consider the IP protection. Now, because they didn't consider this, they approved the case or the components inside which are not protected with this, which are not certified for being an IP protected components. So they will have to redo the entire. They actually redid the entire stuff again, and that took an additional 3 to 4 months of time. And that is something that we should always avoid. Our target market, what is our target market, and what is the compliance that is required in that specific thing. So that we should always be aware of. And then also trying to know the technology readiness levels. This is a measurement that is used by a lot of European space research organizations and also a lot of R&D organizations in India as well. I'll just quickly go through this. Basically, many times with researchers, PhDs, or any of these people or people who are doing a project, if you ask them what is the how much is your project complete? The most frequent answer that you get is you get number 60%, 40%, 90%. Is that a common phenomena that you guys also have heard of it? Yeah. Okay. So yeah, at least I've heard that way too many times. So that's the reason I make it a point to communicate on this one. As in, what 60% is for an electronics development guy, it is not 60% for a firmware guy, and then it is not the same thing for the guy who's building, probably if it's collecting data at the database guy, and the mechanical enclosure guy probably is at a 0 level. So this measurement, what it basically does is it helps you compare against the standards and also communicate within the team or across the teams, as in to what level the validation has been done and to what level the product is ready, as in to launch the product. The sole goal of this one is if you have to launch the product, so then you come back. Basically, TRL 1 is basic principles observed and reported. Then TRL 2 is technology concept or application is formulated. That means you're put in the requirement document. And here in TRL 3, your experimental and critical function, you do a proof of concept, you do a POC. That means you're at TRL level 3. Okay. And component or a breadboard level validation in laboratory environment, TRL 4. So like this, TRL level 9 is when your product is actually ready. So we always use this terminology internally to communicate, as in to know where the product development is or where the project progress is. We always believe this is the best method to understand. And yeah, any queries till now? Yeah, I can move it.
Yes, Sudhir.
Yeah. Okay.
Sir,
Okay.
can I interrupt for a moment?
Yeah, sure.
These levels that you have mentioned,
Hmm.
in general, how long does it take to go from level 1 to level 9 for a general product?
Okay, I'm going to cover 3 case studies. In that, the average time that we took for one product from TRL 1 to 9 for one product was 7 days, actually 6 days or less actually. And for another product, it was about 30 days. And then there is another product which took almost like 8 weeks.
Oh, okay. Thank you.
Okay, and this and we are normally regarded as that we deliver pretty fast, and we are able to do at that speed because we have everything in house. That means we have a design team, we have a prototyping, we have injection molding, we have CNC with us. Okay.
Excuse me, I have one question.
Yeah.
Have you developed any medical devices?
No, we have supported for medical devices for enclosures,
Okay.
but we have not developed any medical devices. We have done UV sterilization units. I don't think it will categorize as a medical device.
Yeah, it doesn't. Suppose like these levels you are talking about, if we start developing a medical device, the regulatory affairs also have to be put in some level. So where do you think that will fall?
So that will fall only at after the at TRL 7.
Okay. After the prototype is developed, you go
Because
for
unless a
regulatory affairs.
prototype is developed in the actual environment, as in, okay, just to run you through, I mean, I'll just take an hypothetical example as you asked. So let us say you're developing a ECG monitor. or a multi-para monitor, which I believe all of you know. A multi-para monitor for let us say for ECG temperature and say SpO2, you're developing a unit. Okay. Now, when will you be able to go for regulatory? After you've frozen on the sensors and you have a proper enclosure and you've tested at least within your lab or with your known people in normal conditions. Only then you'll be able to go for a regulatory compliance. Like for example, if you're going for a CE certification, your CE certification will require you to document all of your components and also what are the risks involved and all that you need. So you'll not know until TRL 7, you'll not even know that what you're going to use. I'll tell you why you'll not know is many times, I think that's the next slide as well, but I'll just skip that because you asked. Okay, many times what happens is, let us say you pick a battery or you pick a specific component at a prototype level because it's available in Hyderabad or because it's available in Element 14, you bought a component. And once you bought the component and you made a prototype, the moment you are ready for the production, many times the product goes obsolete or the product is not available in the quantities that you want. Does it sound familiar? Does it happen to you as well? It happened to a lot of our clients. Yeah. Hello. Can you hear me?
Yeah, I can hear you.
Yeah. So it happens pretty frequently. So you'll not know or you'll not freeze on the components or the structure of it until you cross TRL 7, because your sensors might not be available. The target price, for example, I can get a PT100 at a much cheaper price. Let us say at say a PT100 thermistor is what, like I can get it at less than 100 rupees. And if I use a Bosch sensor for the environment and for CO2 monitoring in the environment, the same one is going to cost some 3,500 rupees. I'm talking of unit to unit, 1 unit of this, 1 unit of that. So let us say your investor tomorrow, or if you're a startup, or if your your buyer says, my total budget is itself 5,000 rupees. You obviously cannot use those kind of sensors. You'll have to go for a cheaper alternative. And you'll not get that feedback unless you show them the product.
Yes.
Yeah, I mean, does that answer your question?
Yes, thank you.
Yeah, thank you. Okay, right. And then, yeah, like many, I mean, this happens with almost, I would say, 90% of the customers that we have. And the beauty is, we tell them that these are the mistakes that happens with 90% of people, but still people do that for various reasons. Okay, first thing is whenever they're picking a manufacturing, they will do this. They have a hammer and they try to use hammer for everything. As in, I've known people using for a simple a timer circuit. For using a simple timer circuit, they try to develop a great they build a breadboard and then they try to get a PCB done and all that, while the same timer circuit is available at 400 rupees or 500 rupees in the market, a ready-made product. That is just one component in your entire system, but you still, because you know a product or a PCB development, people try to redo that. And even we did that. I'll tell you in the case study, even we did that. We are no exception, but we did that. And also people who have a CNC machine, they try to get everything done using CNC. People who have 3D printers, they try to get everything 3D printed. I'll tell you one funny example that we got. Okay, we got a requirement from a customer asking for a cylindrical shape to be 3D printed, which is about 10 inches height and they want about 4 holes on the sides, about 6 holes on the sides. Okay. And the wall thickness, they specified it as they gave a drawing and all that. So the wall thickness also they specified a cylinder with holes. Okay, and they want it in plastic, and they wanted it to be 3D printed, and they want about 40 units of those things. Okay, what would you do normally? We have 3D printing, we have CNC. What would you do? Normally you say, okay, you design, this is the cost. But then the simpler solution for that customer was to buy a PVC pipe available in the market and make holes using a regular drill bit. But just because that guy knows 3D printing and designing, they want to design that. Okay, what it does to your projects is this kills away your entire time. And your time to market, it expands like crazy. Just because we know something, let us not try to do that. We should do it only when we really need that for that specific project, because that project is our boss. Most people may not like this, but unfortunately, that's a reality. Let us move to the next slide. Yeah, and don't do overkill just because you like. When you need this, when you just need this, don't build this. Frequently committed mistakes. People go to investor pitches with components like this. I mean, that would say that will give you fetch you much lesser valuation, or they will think you are just a hobbyist. When you compare this with a properly enclosed unit or properly planned PCB, it looks much better that way. So this is, at this stage, you are only at TRL 2 or 3. So ideally, you should be pitching at TRL level 5 or 6 kind of a level, rather than at this stage. Okay, and what happens is many times there is a loose connection. Then you say, okay, this is not good, but we'll make it good and all that. So people will obviously understand, if there is somebody looking at an entrepreneurship, then they will understand that, okay, these guys are not really serious about their product. They will not think through the product. Then you have the PCB ports. You guys can see the USB port is popped out of the board. This gap is where the enclosure sits. If this does not happen, like about few years back, there used to be some Chinese phones wherein the USB ports would not penetrate into them. You'll have to use their USB ports with a longer metal piece extension. Okay, the micro USB ports. That is because these things are these are not planned properly, as in the USB ports are supposed to be at the edge. The metal has to touch at the edge. If you look at your phones, you'll understand the metal will end at flush with the enclosure, the outer enclosure of these things. And one more thing, remember in the previous slides, I've talked about the ingress protection. The ingress protection is wherein you need water protection or dust protection from various sides. Now, when you're building a PCB or anything, what happens is many times that you try to build the ports in all directions. Like, for example, a USB here, another here, and then there is another port here, and then there is another port here, and then there is a power cord here. Now, what happens is all 4 sides of your device, of your product, are there is some or the other port. How are you going to mount it onto a unit? It is very difficult. Like, for example, if you see any well-developed product, the ports are on a single side. Earlier, the phones used to have head jack on one side and charging port on the other side. Now everybody moved on to one side for 2 reasons. 1, usability is easier. 2, they will have to protect only one side for the IP protection instead of protecting all sides. And that will also make the injection mold very, very complex for you to develop it. It is very easy for you while designing the PCB that you put the ports in all different directions wherever possible. In fact, this PCB is a classic example. 1, 2, 3, 4, and 5th direction on the top also. That means unless other than keeping it on the ground, there is nothing you could do on this. If you see your internet modems, all the ports are on single side. The indication is on the opposite side. Imagine 4 ports coming from 4 different directions. How are you going to even place it, mount it? It is very difficult, or it's not usable rather. And then giving the feedback, like for example, if the camera is working, then there's a small light, subtle thing, but you will notice that your camera is on. And then there's a magnetic feedback or a haptic feedback or an audio feedback. And always try to design your products with idiot proof, like SIM card. People will always misuse it. So you have to be smart enough to make your product idiot proof. Okay, and then within the technologies, I think I've already run through these things. These are some of technologies that we frequently use here at IMEC. The FDM, which is using filament that we use. The filament is heated and then extruded layer by layer it is built. SLA, as we have talked already, this laser is shot here and then it's printed inverted mostly. NUSLA method is also brought by a company called 3D Systems, wherein the SLA is not inverted, it is straight. Okay, that is helping a lot of gravity. Because of gravity, whatever you're losing, and then the peeling off happens. So that is being prevented by that company called 3D Systems. It is giving a pretty good output for SLA. And then DLP. This is again, an image is projected on a screen or using a regular projector, and the components are made. Again, the liquid is poured and liquid is cured with light. SDL is, as I told, the layer by layer, sheet by sheet, and this is cut and repeated. So this thing is almost on the verge of extinction because there are not many tools for this technology. The advantage of this thing is you can make full color products like this. We have this technology in-house at IMEC. Okay. And then you have composite fibers wherein you can make a very hard, very strong components, and you get for a very lightweight, you can get a pretty good strength. I mean, you can get an aluminum equivalent strength at probably half of its weight. So, and then you can also do with Kevlar. Kevlar also gives a great abrasion resistance. Kevlar is a material, proprietary material by DuPont, and Kevlar is the one which is used in most of your bulletproofs. Okay, fiberglass, most of you must have seen the bodies that of many buses or these FRPs. These are again most boats. They are made using fiberglasses. So fiberglass can also be used in 3D printing. And these composites, there's a company called Markforged, which leads it's almost like a global leader in terms of composites. I've been fortunate to visit their headquarters once in Boston. So pretty amazing parts that they make and great strengths that you can get. And the customization that they offer is next to none. If you see this component, I got this component done in front of me. The black part is carbon fiber. The white one is nylon, and these are threaded inserts. This is a bike brake pedal. So this gave an it has an amazing. I still have this component with me. It's been like 4 years now, but it's an amazing component or amazing strength that this company can give. So composites is one rare application. Very few people wherein the weight is a critical thing. Like for example, you want to build a limb for someone, for them to move faster, or say you want to build fingers and somebody has an amputation, you want to build something like that. And composites could be your answer, wherein you can get a great strength, good durability, and also abrasion resistance and lightweight. So it's a great combination. I thought I'll share it with you since it's mostly biomedical department is there. Then you have investment casting. With these are some of the jewelry that we casted. This was specifically for some custom use for antique of movies and all. Okay, sand casting also we have done. So yeah, these are miniatures that we built. We built miniatures for this Hyderabad Metro as well. Yeah. And then these applications and all, I think you must have been bombarded by now already. Yeah. So yeah, then let us move to the case studies now. Okay. Any more questions till now? Okay. We'll move ahead. All right. Okay. Now, this is for making any product in bulk or launching any product. This is our standard process that we follow. We first think of what's the need and understand the need, and then we make a design using CAD. Then we mostly 3D print because it is the fastest way to make. And if something is readily available in the market, we use it. But otherwise, we 3D print that, or using CNC, we do it. And at this stage is where we go back many times to design or even to thinking. Like, for example, once you start making a prototype, you realize that this product won't work. Or you realize that this product is already available in the market at a much cheaper price, which you might not be able to match. That is also an important aspect that you should consider, that you need to be constantly vigilant about what products are being made in a similar area, or who else is making this, at what price, and how they're making it. That is a critical component for you to launch a product or launch a business rather. Okay. And if there is a design feedback, then we design again, we take the feedback, and then we reprint it. And then once this 3D printing is done, then we move to mold or tooling. Like, for example, right now we're doing something for a dental group, wherein we're making silicon-based parts. We made a silicon tooling using 3D printing, and so that is our tooling there. And then we make remaining parts in 3D print, we join them, and then give the product to the customer. So in other cases, you make an injection mold, you make plastic parts, and then you start making bulk, and then you also design your packaging and stuff, and then launch the product. For example, it's a metal punch, then you first you 3D print, check the fitment and all, and then do a tooling properly, and then you launch the product. If things are not working out, ideally you should be able to do it, or rather I should say print, or maybe this is not completely correct. Probably I should say prototype. Okay. Yeah. So print or prototype, and then molding and tooling, and then and then you launch. Yeah. Okay. And then let's move to the next slide. Okay. So we when COVID hit, we were asked by we got an opportunity to make face shields for these things. Within like 6 days, somebody asked me that how much time from TRL 0 to TRL 9. This product, we took it in 6 days. As in, we were in 2 days, we started the design and stuff, and then we started 3D printing. I'll just walk you through the process. And by default, whenever you're making something, you have to look at these things: the fit and function, the aesthetics, packaging, production, cost per unit. These 5 things is something that we need to check when you're moving a product that you intend to launch into the market. Okay, so I'll tell you what we have done at this stage. Okay, this is the design. Let me show you the design. You guys can see the screen as well?
Yes, sir.
Yeah. Okay. All right. Okay. So this is the design. This is the 3D design that we have built. And okay. And once we built this design, when COVID hit, the masks were in a shortage, and also the people needed this protection because this is a face shields are made using a non-porous substance. Because it's non-porous, this will not penetrate. The particles will not penetrate, and the breathing also is relatively easy if you're using this. But many doctors use this as an added protection over their masks. Okay. Now, Okay, now coming back to this design. So we made this design. Once we made the design, okay, what do you check? We check on the fit-in function. Okay, the fit-in function as in, does it fits majority of the heads? We tested with about 40-50 people whether it's fitting the thing or not. And then aesthetics. Aesthetics as in, we wanted to have a smoother curves instead of having a bulky pieces here and there. So we wanted to have a smoother curves, and these 2 points were meant to hold it by 2 fingers. Remember those days when we were afraid to touch anything? Yeah, it was not quite long ago, so most of you must have remembered that. Okay, and then when you're talking of aesthetics, we also, since it's our product, we wanted to have our logo. And when we wanted to have our logo, I'll tell you, like for example, if you see below this, we have something called as an Ideas to Reality in our logo. Now, while we were making it, the Ideas to Reality would fit here, but to do that, you'll have to decrease the font size. And to do that, the mold making would require a laser etching. Since it was lockdown, the laser etching was closed. So we compromised on that. We took a trade-off on that, saying that we'll make the font bigger and just give our website. That will also help us making the business. Similarly, if you're looking at this logo didn't go into production. The RCA logo. This is a pretty complex logo. It looks great on the design. Even 3D printing cannot produce it. And if you have to do it on an injection mold, it would require this logo alone will take an additional time of about a week. So we made a trade-off that we are not going to do this one. Okay. Now, but we maintain the logo, the text on either side. Okay. And also, yeah, fit-in function, aesthetics, and then packaging. Packaging as in, we want this to be as flat as possible, so it doesn't require. It can be packed. It can be stacked well, and it can be made into bundles of about 25 units each, and then given to respective doctors and hospitals. And then we have to look at the production. Can this be made in mass production? So we made a mold for this, and the mold was able to make about 5,500 units per day. So once you get the mold done, there is nothing you could do because you could do only minor changes. Okay. Yeah. And by the way, we got the text on the other side as well, wherein the government wanted to thank all the healthcare workers. So they wanted this with thanks for your paramount service in defending mankind. So this they wanted it to be there. Now, and also cost per unit. Now, to reduce the cost, what did we do? Okay, the thickness initially was much higher, so we reduced the thickness a little bit. Now, just to give you a context, this component alone, this weighs about 17 grams when it is made using injection molding, and it weighs less when you 3D print. Okay, because there is a lot of hollow gaps in there. Okay, when we calculate the 17 grams, in total, in the last 1.5 years, we made at least about 2 lakh units of this. Now, imagine if this 2 lakh units, the weight is increased by say 5 grams per unit. So I'm talking of 1 million grams. So if I'm talking in kilograms, I'm talking of 1,000 kilograms, which is 1 ton of material which was not needed. So when you are going for bulk production, every gram that you can shave off, especially in products where an injection molding or where these kind of things are there, you really need to shave off every bit which is not needed. You need to shred all that weight. If you don't do that, your product becomes unviable, or it becomes, there is no need for that. When there is no necessity, the obvious logic is you shouldn't be doing it. It will be an overkill to do that. Okay. Now, okay. So then we designed this. Now, after we designed it, Yeah. Then we also, I mean, there's another part of it. The other part of the game is how do you market it, how will you package it for customers, how will you package it for institutions, and how do you package it for international customers. We got some international orders, but we couldn't send it because our package didn't meet those standards and it was taking much more volume. Okay, had we planned this one better, we could have probably, instead of 2 lakh units, we could have sold 2 million units. But we didn't plan that because of lack of experience or lack of knowledge. We didn't plan that. So that is one example. Any questions on this case study? We'll go to the next case study. We can move.
Yes, Sudhir.
Yeah, man.
What about the transparent sheet part?
So transparent sheet is taken care normally by the that is die punch, madam. Regular you have this wedding card, guys, no? So okay, I'll just show you that as well. Okay, if you see this transparent sheet, ma'am, this is actually polythene sheet. We used projector sheet initially, then we used rolls. So this is there's a die punch. Like for example, if you see all of these fancy cards that you see in greeting cards or your wedding cards, there is a typical die punch which is used by printing. If you go to Lakdi Kapul, the entire industry is that. So they were able to cut this one as well using the same method. They put a sheet and then they cut it manually.
Okay.
So there is a die made with holes and this rounded corners, so it does not pinch. And the sheet that we use also varies. You can use a 100 micron thickness sheet. We can use 175. People have used 350 microns also. But we stuck to 100 micron sheet because we wanted this transparent sheet part to be disposable. Because if it's if you are using it, we are expecting that this has protected you and there is some virus on this. So we expect that to be thrown at the end of the day and then use another one.
Okay.
The thicker one, what happens is it's expensive and people tend to use it for longer time. And that defies the logic because you are carrying your virus with you into your home.
Yes.
It is like you're collecting everything that's there and then carefully taking it to home. Okay. So ideally this is supposed to be rolls. That is how it was designed. Yeah. And then coming to this one, there was another product that was asked again by in our discussion with DRDO that we wanted to design a door opener wherein we don't want to touch, or a lift opener. So what we did at the time, I don't know, a lot of people must have seen these hooks that people have made, wherein there's a small keychain kind of a hook, or people are using key and then touching lift doors or pushing doors using that. Now again, that also defies the same logic that you're again putting the same thing back into your pocket and making contact with your clothes or with your handbag or with your hand. So our logic was that this does not fulfill the purpose. Let us do a retractable design. If you can see closely here, there's a spring. So this one is spring loaded. So this one moves forward and then you operate it and this goes back completely inside. So you don't make a contact, you can wash it whenever you can. And we also given a yo-yo so you can extend it. You don't forget it and you don't keep it inside. It's always on the outside of your clothing or your bag or whatever. Okay. Now I'll tell you the few challenges that we faced in making this one. Same thing, again, we checked for the same thing: fit and function, aesthetics, packaging, production, cost per unit. Okay, let me open the design link for you. So it's easy. Okay, you can see the design now.
Yes.
Okay, all right. So I'm just giving an exploded view right now. You can see the exploded view, ma'am. Everybody?
Yes, Sudhir.
Yeah. Okay. Okay. Now this is a little complex design. If you see the previous one, it is fairly simple one. It just had one injection molded component and then you make it. So and also the need was so high at the time. We were even 3D printing simultaneously and giving the face shields. Now, by the time we started making this one, people got a little bit relaxed, and the complexity of this product is increased a little bit, as in it needs to be spring loaded. Now, again, when it's a spring loaded one, how do you choose your spring? It doesn't have to be too strong that it hits back and or it's difficult to move forward, and it also has to be corrosion resistant, because you're going to wash it or you're going to use sanitizer on it. People were throwing everything into sanitizer and bringing it out. Okay, so we got this corrosion resistant the metal wires, the spring steel, and then we made the springs with that. Okay, so we loaded the spring inside. Now, if you see the number of components here, you have 1, 2, the one which moves inside. Okay, and by the way, this sharp one is to open the packages. This one is to hold, and this one is to press the buttons. Okay, and this is a different injection mold. This is a different injection mold. These two are one set. This is one set. So 1, 2, 3, 4. 4 injection molds. One spring being made customized for you. That too with the corrosion thing. So this one took more than the first injection mold to be ready. It took about 31 days kind of a number is the time that it took. And yeah, I'll show you. If you see this one, this is 3D printed, entirely 3D printed. This is injection molded. Obviously, this has great finish, but using this, we made the design, we refined the design a much better, and we also were able to test and see if the product was working. It was able to cut the packages, it was able to open the doors, does it have enough strength and all that. We were able to test using 3D printing, and then we moved. Once we made injection molding, we were able to make about 1500 units per day. Again, same thing. How do you check the fit and function? Fit and function, simple logic. In this design, does it fit the pockets? Does it fit the jeans pocket inside? Okay, and whether it's giving the function. And then aesthetics. Aesthetics as in, does it have proper round corners? Does it hurt? Or when you're pulling something, if it's sharp on your hand, that might hurt you. So those aesthetics have to be taken care. These also have to be good rounded corners. And this is supposed to be, to make it easy to carry, we wanted to make it like a keychain. So that's the reason we are able to wear it like this or use it as a keychain with a ring. And then packaging, since we learned a little bit of lesson from that. So for packaging, I'll just give you an idea. Like, for example, one thing, let us say you're doing a cardboard packaging or a blister packaging, like your tablets. The papers or the sheets that the packaging industry uses, they are of the standard sizes. What happened while making packaging for this one is the outside box. I think the outside box, it was just because it was about 4 mm higher, we were getting about 8 to 10 units, about 10 units lesser for each sheet. That is increasing the cost significantly. So when you're designing or launching a product, you have to plan in all the directions, wherein your actual component inside the function, then, and for all of these things at a 3D printing and a design stage itself is where you will have to consider those things. If you don't consider, you will lose a lot of market like we did. And by the time we did, people who are good at that, they copied this design and sold it much faster, especially face shields and this stuff. Okay. Yeah. Again, production and then cost per unit. Cost per unit, as in, for example, if I'm increasing the size of this one, again, the same logic applies. Even if I'm increasing it by few grams, it increases drastically. So you have to multiply by, say, 1 million units or 1 lakh units kind of a number, then you will realize what is the cost per unit. Okay. Yeah. So any questions on this? on this case study, anything that you can refer to your case studies that we can discuss? Okay, we'll move ahead. Yeah, then we made a UV sterilizer. This is the complexity level is much higher in this, and here we have chosen to use entirely a sheet metal system because it is supposed to be in a sterile environment, and when compared to that, the UV sterilizer has a much more complex components, as in it has literally about 110 components inside it, if you include all the screws and everything. And this has these 4 UV lamps. Okay, I'll tell you a couple of two cases, two instances wherein it delayed this project drastically. The number one is, how many of you have a tube light in your room right now? Many of you must be having a tube light. You will never realize until you hold multiple tube lights together that all tube lights are not of the same length, even of the same company. They vary by plus or minus 5 to 7 mm, the tube lights. Now, the disadvantage of that is when you're mounting them vertically, you cannot have a fixed base below. You need to have some flexibility. And that is the reason why tube lights are having those metal flanges on the edge, wherein it can move out a little bit. That means it is planned for the minus 5 or minus 7 mm. And when you push that and then twist it, it can move by about 10 mm, 5 mm on each side. So it can fit the tube and still have the contact points. For us to even realize this point, it took us quite a lot of time. And that delayed the product launch almost by a month. And then, remember I told you that people do just because they can build PCBs, they will build. So we did the same thing. All we wanted here was a timer to switch on the lights and then turn it off. But what we did, during lockdown, we put pressure on some people and then we got the PCBs manufactured and got it done. But then we realized the components were not available. Then after doing all this parallelly for almost like 4 weeks, then we realized how stupid it was, that the timer is available ready-made in the market, and it's already CE certified. So I bought those. I rather buy that one and then put it in this, and then develop my own thing, because there is no value addition if I develop a timer by myself. For me, what's important is, I mean, just to give you a number that sticks onto your mind, we could have made ₹1 million more if we could have made this product a month before. Just because of our stupidity that we didn't realize that the simple thing that we could buy something and then put it inside our thing, our unit, we made this mistake. And then another mistake, a third mistake also I will share with you that we try to make. This unit is much smaller here. Okay. Okay. The design initially actually is much bigger, wherein it has a human detection sensor, because the UV light is not supposed to be exposed to, I mean, humans are not supposed to be exposed to UV light. We built a sensor. Okay. And when we were trying to fine tune the sensor, that itself was taking a pretty long time. We realized after toying for almost 2 weeks just on that sensor, the proximity sensor, we realized that the people whom we are selling are smart enough, and we can launch that at a later stage. That can be a second version of the product wherein it has a sensor. Right now, what we did, we put a delay timer and then we put a timer for switching and all. That means it will give a beep and then start after 1 minute. You're supposed to go out, use your common sense and then go out. And then we put stickers on all 4 sides. It's not visible here, but we put stickers on all 4 sides that you should go out. And we launched it without the sensor. And we fine tune the sensor much later. Okay, these trade-off decisions are something that you will have to take during your product development. And let me tell you how designing and prototyping will help. Now, had we not had a design and a prototyping capability, this product could have taken maybe 6 months or maybe 7 months for our capability. Because if I have to get this designed each time design iteration will take about a week, and we did at least some 7 or 8 iterations in this, and that will delay the project much further than the regular development. So yeah, I think this concludes the basic, the third case study that I wanted to share. And this unit has a lot of 3D printed components because it's not being bulk manufactured. It is made in only very few quantity. It is made in sheet metal because sheet metal, steel is trusted to be, normally it can be cleaned properly and it can be sterilized properly. And anyway, there's a light that's happening. We need a non-porous and long-lasting material, so we picked this one. For aesthetics also, we wanted to make it look good, as in to make it look little futuristic. Yeah. So, and if you see the labels also, we have got it done using laser etching, DUTI or your iMake or CE certification and all that. We got it done using laser etching because laser engraving lasts forever. Your stickering and all will go away quickly, but this will remain forever. Yeah, and yeah. Any questions on this one? Okay, I'll share this one. These are general. Also, when you're making designing and stuff like designing and 3D printing, it is very important for you to know what 3D printing technology you're using and what that 3D printing technology cannot do. That means I'll give you just 2 or 3 examples because I've exceeded my time, I believe. Yeah. If you see,
you have 15 more minutes, no problem.
Okay, all right. Right. All right. If you see the FDM can do this wall, the supported walls, only at a 0.8 mm. If you want something lesser than that, you will have to go with SLA, stereolithography. If you want, let us say, an unsupported wall, the 0.8 mm again is the maximum thickness, the lowest thickness that you can go. Now, these are the things that you need to consider while building the product and also while designing. That means while designing itself, if you go back to our TRL slide, yeah, you should know whether you are designing for TRL 3 or whether you are doing it in the actual TRL 7. That means if you are doing for 3D printing, your thicknesses have to be, there's got to be a minimum thickness that you have to achieve, you have to allow in the design. But if you're going for injection molding, you can lower that thickness because that will save you money in long term, and because injection molding is much stronger for the same material when compared to this thing, you can afford to lose a lot of weight in injection molding. So you need to have this clarity as in at what stage you are and at what stage and for what you are designing. If you're designing for an SLA, this is nothing but what people are calling this as a DFM, design for manufacturing. Okay, we often face this problem with a lot of this film industry when in film industry they use mostly Maya or other 3ds Max, these kind of stuff, wherein they are not designed for manufacturing, they're designed for display on the screen. Okay, now that care if you take, your iterations will be much faster and you can leverage 3D printing and designing to the maximum extent. So these are the limitations of various 3D printing. I'll just go through for one technology because I cannot go through all of them and you'll not even remember all of that. Unsupported wall structure, 0.8 mm. Support or overhangs, 45 degrees. Now, you should also remember how you orient your parts and print. And whenever if you're designing and somebody else is printing, you should also tell them that, okay, this is the orientation I need more strength in, and this is the orientation that you should print to avoid getting supports. You should also mention which direction you need good surface finish, because based on that, they will place the object on the 3D printer in that direction and supports on the opposite direction where your finish is not critical. Again, remember we talked about embossed and engraved details in our face shields design, which is this. Yeah. Okay, this is an embossed design wherein this was not possible at the time. So we made that compromise. We made the design, but we realized this cannot be done, and then we dropped the idea. So we took the trade-off decision that, okay, this will delay the whole project, so let us drop this off. Okay, so again, embossed and engraved details, 0.6 mm wide, 0.2 mm high. It has to, whether it's lower or higher, this is the minimum thing. Horizontal bridges, that means printing without the supports, the maximum is 10 mm, and all others cannot do except the DMLS. And holes. Okay, what is the hole diameter? It can be successful print is 2 mm. Connecting or moving parts, what is the clearance? 0.5 mm. Escape holes. Okay, so escape holes is not relevant in FDM because escape holes is relevant only liquid-based or powder-based system, wherein it is the loosely binded powder, the loosely unbinded powder or your liquid needs to escape from inside of the part. I'll show you an example. Where is it? Oh yeah, this one. Okay, if you see this product on this side, there is a lot of intricacy for this jewelry, this bracelet. Okay, what happens is if you don't orient it properly and don't give escape holes, the material will remain inside and it will not get cured. And because of which, remember I told you there is a gravity factor also. Because it gets printed upside down, the gravity, if there's a lot of weight, this might fall off because you're trapping the liquid inside, uncured liquid inside, and that also tends to vibrate a little bit or move a little bit. And that will also give you a very bad finish. So when you're planning for this design in SLA or any liquid-based polymerization system, you also need to plan how your material is going to escape. If you see on this part as well, this is also made in SLA. These two parts are supposed to be, because we needed greater finish on the inside, we had to print in this direction and give these two drain holes. Okay. Okay, and then pin as in the minimum diameter pin can be printed. Let us go back to our hook thing. You know, to get this pin printed, we need to identify what is the thickness required and how much this thickness is required to actually hold this whole thing with the strength, with the required strength. Because we wanted to move 100 kilogram of gate of an iron gate, so we need that kind of a strength. So we had to have a minimum thickness, but if you decrease the thickness, this will break away. Right? Tolerance as in, again going back to the same model, there is a movement here. If you see the inside this part, I'll go to the design part, I think. Okay, if you see this one, these are very tightly bound. Okay, this moves inside. Let me see that. Inside this, there's got to be a tolerance. So what is the tolerance required? For injection molding, it is different. For FDM 3D printing, is different. For again, SLA, it is different. For each one of these things, it is completely different. So these are the various numbers that you need to keep in mind and various technologies which you might be using. And these limitations are critical because without which what most often happens is the designer blames the 3D printing team or the prototyping team. The prototyping teams tell that the designer does not know how to make for manufacturing. So this, if you don't have this in sync, your project will go in, it will go in circles. Yeah, these are the sources. I've used only one source, external source for these slides, for this slide and the slide depicting the various 3D printing technologies available at the moment. Yeah, I think I'm done. Any questions, please?
Yes, participants, any questions to Mr. Sudhir?
Yeah, ma'am.
No, I was just referring to the participants if they have any questions to you.
Okay, sorry.
Yes, please interact.
Hello, sir.
Yeah, hi.
Are you open to the idea of collaborating with the students of engineering on projects of mutual interest?
Ma'am, okay, let me be little. I'm open, but ma'am, the challenge that I find with the engineering students is their commitment, because we are a startup. We are a small team of 10 people. Okay, and we need people with high commitment, and we can teach people if they don't know, but if they don't have commitment. It delays everything, and it gives a lot of frustration to us. So our experience has not been great earlier with interns because of this reason. Because one day they will say our professor called, the other day they will go to a movie, and then third day they will say they want a certificate.
Yeah, I mean, I'm aware of that, but it is not the kind of projects that I'm talking about is where you collaborate with the faculty.
Oh, yeah. See,
And the faculty is responsible for the students.
Then the answer is yes. Then the answer is yes.
Okay, sir. Then I'm a faculty. I'm a professor from an engineering college at Pune. And I'm interested in working on these projects. I'll be in touch with you, sir.
Sure, ma'am. Here is my contact details. And
yeah, I've taken that.
Yeah, sure. Okay.
Any more participants would like to interact with Mr. Sudhir? Yeah, if there are no queries, thanks Sudhir. It was a wonderful lecture. You have given the entire product cycle. So it was, and also you have shared whatever mistakes you have committed and how to maybe you have overcome in the next product, and the challenges what are going to be faced by any manufacturer. Okay, thank you so much. It was so practical. Actually, it was almost like a practical session because you have showed each and every details of at least 3 products of what you have manufactured. Okay, thanks a lot and, for accepting and yeah, wish you all the best.
Thank you, ma'am. Thank you all. Thank you for the
Just
time.
one question more, if it is possible.
Yeah. No, go ahead.
Where are you based in Hyderabad?
We're based out of LB Nagar.
Pardon, sir, I didn't get you.
LB Nagar.
Hyderabad.
Okay, fine.
Yeah, Hyderabad, LB Nagar. Yeah.
Yeah, okay, Sudhir. Thank you so much.
Thank you, ma'am.
Yeah.
Thank you all.
Yeah.
Bye.
Participants, you can fill the Google form for attendance for this particular session.